resume our session. Yesterday, we could not give you the Excel files that I presented. We will upload all the files in these Excel files and send you the link to you. Here, yesterday, the file that I showed you, the model separation file, one thing I forgot to explain you. For example, in the model amplitude that I extracted, that model amplitude for each mode should be, the unit should be consistent with the forces that you extracted. For example, modal amplitude, if you extract in meter unit, the force should be in kilonewton meter unit. That one I missed it. So all the files will be uploaded, and also I will give you the scaling of response spectrum analysis in this story force file. I have the formula here, and you can see. You can see how to find the scale factor from equivalent static force base shear. But that's final design base shear should not be less than the response spectrum elastic base shear divided by R factor. I haven't checked for that one. If R is 8.5, you have to divide the elastic base shear, which is for example here 43,000 divided by 8.5, and that base shear should not be less than the equivalent, the final base shear should not be less than that base shear. If it is less than that base shear, we have to use elastic response spectrum base shear divided by R. So we will continue the overall response analysis results from our nonlinear analysis. First, after we conduct the nonlinear analysis, we have to check the energy error from our results. All the analyzed models are in your computers. You just open it and they are already analyzed. And please go to analysis phase and click the energy balance button.
The analyzed model for if you want to see the results will be, if you see the folder AIT workshop seminar, right? Day 4 and Mr. Ong's name, and then the hands-on training model. This is the location for the analyzed model if all of you want to open your analyzed model, because we'll be showing the results in analyzed model, and if you want to open it, you can open it from this location. Okay.
So after you open the model, go to analysis phase, this button, and then click this energy balance check button. First, we have to check the energy error percentage. Here, the energy error percentage is 1.19%, which is in the acceptable range. If the energy error is more than 5%, we have to recheck the model and fix them, and then we have to rerun the analysis. Now the energy error is okay. That energy error is the difference between input and the output energy. Then we will go to another tab, here element groups. Then we can select the element group that we have defined. From those groups, we will check each group how much energy is dissipating from each group. First, I will select the shear walls. Then click the plot button. Here we can see that shear wall is not yielding at all. The y-axis is the percentage of the energy dissipation from that selected group. Yellow one is the energy dissipation from that selected group, but the yellow line is very small at the bottom. But the red one is the total energy dissipation. The x-axis line is the duration, time, earthquake duration in seconds. Then we will check the coupling beams. Select the coupling beams. Now we can see the yellow color. So at the end of the ground motion, the coupling beams group is dissipating the energy about 17% of the total dissipated energy from this graph. Then we can also check for the girders. Girders are yielding a lot. Here we can see the girders are yielding approximately 82% of the total dissipated energy. So from these graphs, we can qualitatively assess the members whether they are yielding or not, before we check into detailed rotations. Based on these plots, we can determine that the shear walls are yielding or not without checking the strain values. Then we will go to see the building deform shape.
Okay, so let me just wait for the plot to be generated, and I'll explain to you about the yielding in the shear wall. So when I already spoke about the previous strain gauges that we had assigned to the model to check the performance of the wall, I had discussed that we already put some strain gauges which will give us the value for the DC ratio of the strain, right? Now the DC ratio for this plot being used is the steel strain DC ratio or the tensile strain DC ratio, right? And if I will continue the plot, now this is the deformation of the structure as the ground motion is progressing. You will see that after a certain amount of time, the colors are already forming in the strain gauges. Basically, these colors show the DC ratio. The green color over here represents 0.2 DC ratio, right? Now, if you start to see some red color somewhere, okay, you can see the red color over here. You can see that that red color basically means that the strain is exceeding the limit that I provided to the strain gauge. So to the strain gauge, the limit that I provided in the model when I was showing you about the strain gauges was 0.002. So this red color basically over there means that the tensile strain is basically exceeding that number that we provided over there. So we can safely assume that the wall at that location is yielding, right? Now in this model, we can see that the wall is only yielding at the base. There is no yielding in the upper region of the wall. Normally, the yielding of the wall inflection at the base will always happen when the wall yields in the first mode, because the moment for the first mode is high at the base, right? If you see some yielding high above, that will correspond to some higher mode effects. But this building does not show a behavior like that, right? So this is about the strain gauge that we spoke about when I was showing you the modeling part. So we already spoke about it, and now we can see that we can get some results for those strain gauges that we had already assigned, right? The plot that you see over here is just the color, if you want to see, or if you want to put in your report or something like that. But generally, we will not use this plot to check our results. We have to know the number also. The color is not important. Color is just to show over here. So when we need to extract, we will extract the DC ratios for the strain gauges also. There are ways to extract it. I think just the same option that you see on the top. Yeah. Okay. So now the other thing is the other option that I will show you over here is the rotation in the girders. So I already spoke about the limit state. When we talked about the limit states of the girders, I already said that we already have defined some limit state. Now, if we want to use that limit state to get the DC ratio, we can use that limit state. I will show you the colored plots of the girders also. Now, you can see the numbers that are mentioned over here in the ratios that are same in here. The light blue color responds to a DC ratio of 0.01. If you remember, yesterday I spoke about the hinges being rigid plastic. Basically, the hinge will not have any rotation if the moment is not exceeding the capacity. That's why I put a very low number for the rotation over here, just to show you that if there is a little bit of rotation, the DC ratio will be 0.01, and then you can have some color forming over here corresponding to the fact that the beam has started to yield, right? And then you can have some other colors also. The DC ratio of 1 basically will mean that the deformation capacity that are assigned to the hinge has been exceeded. If you remember the numbers that I used, some typical numbers 0.025, something like that will be exceeded, right? So I will plot this one for you over here. Okay, we need to give it some time to plot, and then you can see some colors also. Okay, so now the results that you're looking at are the DC ratios for the rotation. As soon as you have a blue color, you can see some blue colors forming somewhere, right? That basically corresponds to the girder yielding. Now the girder moment capacity has already been exceeded. The green color that you see in the building is for the DC ratio of 0.2. So if your rotation is capacity is 0.025, you multiply that one with 0.2, you get the green color. So you can know that the number is exceeding that number of rotation. But you will see that, and that you will not see any red color over here. Basically meaning that the rotation that I already defined in the deformation capacities is not being exceeded, because the red color will correspond to the DC ratio greater than 1. And currently we are checking the DC ratios of rotation, right? So this one is the rotation over here is exceeding 0.2 times the deformation capacity that I gave them, but not exceeding fully. So if it is fully exceeding, the ratio will be higher than 1. You will see some red colors forming somewhere. But right now we are not seeing any red color forming anywhere. So basically, the rotation is there. The girders have yielded, but they have not yielded significantly enough. Right? So yeah, only this one. And
Shabir, ours doesn't have a dot.
Okay. That one is, you have to select this option over here.
Wow.
I just selected this option just to show you that you will
Okay.
have a top, have a dot. Otherwise, you will just have a red color or blue color. You just need to select this option. Components are colored, frame elements only. So the component will be colored, the element will not be colored. So just to show you this thing. Okay. This one is also something that we would like to check sometimes to see what is the behavior of some components or some actions that we have modeled as linear. So as you remember, we modeled our columns as completely linear, right? So now if you want to check the column forces throughout the time history, and so by column forces what I mean is that the forces of this column throughout the height of the structure, you can use this option over here. The option is called moment and shear diagrams. It will plot the moment and shear diagrams of columns for you. You can have a single element option, or you can have a line of elements whereby you can select many elements, and the moment and shear diagrams for all of those elements will be plotted for you. So I think if you guys want to open this tab, you can open this tab also, and then try to follow so that you can get the same plot as I am getting. Right? The tab over here is the moments and shear tab, shear diagrams, and then you need to select the line of elements option. Line of element basically means that multiple element results will be shown together. A single element basically means that you will have a single element result, right? And also, if we want to see the histories of the forces, we need to select the option to show us the time histories of the forces. If you select the first option shown in here, this will be only envelope forces, right? And if I want to select the column, I will just drag over the column like this, and all of the columns below are already selected, right? So just plot it.
Okay, from this diagram, we can see the selected column along the height of the building. This one is the moment diagram. This one is the shear diagram. This 1-2 plane is the moment in M3 direction, and this shear will be sheared in V2 direction. as you can see here in the above levels, the moment diagram in this those floors, they it looks like the unsupported span is like from here to here. There is no double curvature, proper double curvature in these floors. As you can see, this one looks it is due to the yielding of the girders which are connecting to them. Now we are passing the peak of the ground motion, so the moments, the girders are also highly yielded, and we are getting large demands. I will show you at the beginning of the ground motion. Now this zone is start yielding, but here in this zone, in each floor we have the double curvature, but here double curvature doesn't have, and it increases larger movement. So in those cases, sometimes if we have the design of the column BMM, vertical reinforcement, we should check that kind of diagram, step-by-step results, not the envelope. If we check the envelope, for example, we will see like this. This is the envelope. This is the moment diagram M3, and this is the shear diagram we do. Now we cannot understand what is happening along the height of the building. So we should check step by step, and if the column moment is increasing due to the yielding of girder, one thing we can do is we should increase the longitudinal reinforcement in girder to prevent highly yielding, so the column moment will not be increased significantly.
This one over here is the plot for the base shear of the structure. You can see the number that we get over here. This will be the shear at the base of the structure. You can see that there is a lot of variation of the forces as we move along the time, right? So basically, the base shear of the structure does not remain constant as we move along the as the time history progresses. Then you can get a maximum number of base shear over here, and then if you want to extract the shear force of all so if you want to get the element results of all of the section cuts that we have already defined, you can get the forces like this, right? So you can, so if you want to extract the results for all of the section cuts, you can go to the multiple sections and then use the select all option, right? And then you can save the histories for the results, or you can just save the envelope results. Normally we will save the envelope results for the section cuts and then save it, right? You can save the file. Let me just save it at desktop, right? Okay, yeah. And then after we have the file already saved at the desktop, you can open the file and then you can copy all of the forces in the file. Maybe start a new Excel if you want to start, because you will need the data in the Excel to post-process it. You can paste the data in Excel. Okay, so after we got the data from the file, we can just copy it. Okay, have you already got the file for the base year or not? If somebody has any issue with extracting the base year results for the analyzed model already, maybe you can ask somebody to help you. So the file that we got from Perform, I'll just simply copy the file, copy the data from the file, and then paste it in Excel. Yeah. Okay, so after you copied the data from the file to Excel, the data is between commas, so you need to separate the data. You can use the option in here, data, and then you can go to the tab of text to columns. The data is delimited by comma, so we select the delimited option. Next, and then the data is delimited by the comma option over here, not the tab option, and then we do next and finish. Right? So you guys can try to follow, to copy the data like that into Excel. So if you will see the data in here, this one is the maximum and the minimum force for all of the section cuts that we have been given. The section cuts are actually shown in the column, right? But the forces are in the row. So what we need to do now is that we need to just copy the data and then transpose it in Excel. So how do we do it? If you want to select the data like that, you can use the Control Shift and then the right tab. Okay, and then you can just copy it. After you copy it, we go back to where the data is, and then from there we go at the top, right? And then select this cell, the cell above level 1, right click on it and then use this option of transpose. Right, if you select the transpose option, you will see that all of the forces are already here. Now for level 1, this is the maximum force, shear force, and this is the minimum shear force. Level 1 section cut, this is the story section cut. Right, for level 2, the maximum and minimum force is already here. Right, for level 3, the force is here. Similarly, for every wall, there is a section cut and then you get the force for every wall over here also. Yeah, so and also if you want to see the units in which your forces, you can see the units over here also. So the units for the forces in the file are Newton and millimeter. Right? You can, if you want to change the units, you can change the unit while you are exporting the data in this location. Okay. Yeah. Okay, so you guys can try to get the data like I have. Okay, so these are the section cut forces that you already got in the Excel file, and then you can use these numbers to do whatever you want to do with them. You can design your shear walls and everything, right? Now I will repeat the same process for extraction of the drifts also. So I will show you how to extract the drifts that we already defined, and then I will save the file and then paste the file in Excel also for you, right? So I will very slowly move to through the procedure to define to extract the drift results. So this was the tab, the section cut tab that you should already have with you right now from where I got the section cut results. If you want to extract the drift results, you can extract the drift results in the drift tab, the tab besides it. Right? You just select this tab, and then after you select the drift and deflection tab, you can go to the multiple results over here, this tab, right? And after we have selected the multiple tab, all we need to do now is we need to select all drifts. You can select them one by one, but the easier option is just press the select all button, right? And it depends upon you whether you want to extract the histories of the drift results, or you want to extract the maximum and minimum results, only the angular results. But just for the purpose of demonstration, I will extract the history results for drifts so that you can see what is the amount of force data that we get for drift history. So after I have selected the save histories option shown in here, right? You can press the save option, right? I will also save this one in my desktop, the same location. I will call the file as drift. And then for the description, you can also write as drift, right? And then just press the save button, and the drifts are being saved. So I'll give you some time for you to extract your drifts also in histories.
Transpose
Okay, so as I showed you, we already extracted the drift results, and when I extracted the drift results, I used the time history option, right? So now what I will do is that I will just copy the data from the drift tab in the drift file and then paste it in Excel just to show you how long the data is if we extract the step-by-step result, right? I will just paste the data in Excel and then use the same option that I used before, text to columns, delimited by comma, and then, right? So what I will do now is that I will move down from the point where the data starts. So you can see that the first column over here is the time step column, and then the next column is for all of the drifts that are defined over here. Now if I move down from over there, you can see that there is a lot of data that we will get if we are to extract the history results. Now I'm continuously pressing the down button over here, and it will still take me a bit of time to reach the end of the data. So you can see that the time history is giving us a lot of data. And sometimes if you have components or actions which have interaction and you need to process the step-by-step results, that one will be very tedious to do, difficult to do manually also. So you can see that I have continuously have my hand on the down key, and then I can still not reach the end of the data, right? I'm near about reach right now. Okay. So if you can see now, I have reached the end of the data. So a lot of data in post-process if you get the step-by-step results for your actions and your overall global results, right? So this one was just to show you the amount of data that you can have if you extract every result from the time history analysis, right? Okay, so moving on, now I will show you one more thing. This is something that we talked about when I was doing the modeling. This one was about the hysteretic behavior of the girders. We talked about it, I show you some energy dissipation factors, right? So what I will do now is that I will plot the hysteretic loops of the girder hinges so that you can see how the loops are forming. The loops that you will see may not be very smooth because the force is not a controlled force, but it is like the ground motion is a random force, we cannot control it, right? So to see the hysteretic plot of the girders, we will go to, okay, from the entire structure view, let us go down and then just select some I think this one does not have any view, so okay, I'll not go to the entire structure view, but we can just go to the tab that is next to the tab that is already open. The tab is called Hysteretic Loops. You can select this one. After you select the hysteretic loops, you can select the group type as girders, right? So I'll wait for you to select this one first. Okay, so after this tab is already open, you can select a single girder, right? And after you select the girder, you can see that you have different types of components in that girder. You have hinges, you have elastic component, but the hysteretic behavior will be shown in the hinge. So you just drop down and then select the hinge, and then you ask the program to plot, right? So you can see that the behavior is something like this. The loops will look very strange to you, but actually, if you see the deformation number over here, the rotation in this hinge is very small. You might think that the loop is very big, but the rotation in the hinge is very small, because if you see the rotation number over here, it looks so small, right? That, yeah. Okay, so you can see some some hysteretic loops being plotted over here for the girder. But these do not look smooth because the force itself is not that smooth continuously. It's not a controlled force. Yeah. And then in this one, the y-axis is the moment value. So if you see over here, the point that I have stopped, the moment value is 682 or 600 and, okay, if I stopped at somewhere, 682.9 kilonewton meter, right? And then the rotation number is 2.5 into 10 to the power minus 5, very, very low rotation. The capacity that I defined, if you remember, the number was 0.025, right? And if I move further ahead, you can see that at this point, the moment still does not increase too much because now the girder has already yielded, so the strain hardening is not that much, but the rotation is continuously increasing, right? So you can see that the rotation at this point is 0.001289, right? So just some nonlinear girder results, and then we can compare the rotation capacities with the rotation demands with the rotation capacities, and then we will have the DC ratio for girder rotation, and then we will check it. Right.
So we have to extract the results in the text files for each component that we would like to check. So for the shear walls, we extract the section cut forces to check the shear wall shear, axial strain values to check the flexural response for concrete, crushing strain, yielding strain, steel, rebar strain, as well as the rotations of the coupling beams, and also we have to extract the axial force, shear force, and moment values for the columns in each group from the text file, and copy to the Excel file for the post-processing. We have to do for 7 ground motions, and then we post-process the results. For example, shear wall shear, we have 7 sets of shear wall shear, and then average them. Then we multiply it with 1.5 factor. Then we check the shear reinforcement. Same thing for the other components. But for the rotations, we just need to extract the rotation values, but no need to multiply with the factor. Then average it and check the rotation limits based on the ASCE 41 criteria. So when we check the column shear design, we have to extract the step-by-step results, but for the shear wall shear check, we do not need step-by-step, just extract the envelope results. And for the residual drift, if we want to check, we have to extract the step-by-step results and then use the last step story drift. So to summarize the nonlinear modeling in Perform 3D, we have to, the difference between EDAPS and Perform 3D is we have to define the member sections, geometry separately, member component properties like the hinges separately, and then we have to compound them. In EDAPS, we do not need to compound them. We just draw the section and assign the hinge directly in the model. But here, we have to compound everything, beams, columns, shear walls, then we have to assign. If we do not compound, we cannot assign in the model. Another thing is, in EDAPS, when you draw a beam line element or shell element, the local axis is automatically assigned. But in Perform 3D, we have to assign the local axis separately. if we do not assign the local axis, we cannot run the model. And mass and weight we have to assign separately in Perform 3D model. In ETABS, after you assign the loads, you can use those loads as mass source in the analysis. But in Perform 3D, we cannot use. We have to assign the gravity loads separately and assign the mass separately. And another thing is, when we assign the mass, we can assign for the tower level, we can assign lump mass at the center of mass location and assign the assign as a rigid diaphragm. But for the podium level, we normally assign the mass distributed manner. And also, we do not assign any rigid diaphragm in the podium level to consider the backstay effect properly. And in Perform 3D, we cannot assign the area loads on the slab elements because slab elements cannot transfer the area load to the supporting beams and columns. In ETABS, you can assign on the area load, live load, superimposed dead load directly to the shell elements, slab elements, and then you do not need to worry for that for distribution. In Perform 3D, so we have to apply the loads to the beams, columns by manual calculation. First, we have to calculate the uniformly distributed load to be applied on the beam, and then apply that load on each beam. So it is more tedious to create a model. Then we have to analyze for 7 ground motions. And in real projects, the ground motions that we got from the probabilistic assessment, hazard assessment consultant, some ground motions are quite long. For example, sometimes number of steps of the ground motions are sometimes more than 10,000 steps. If we run 10,000 steps for one ground motion, it will take a lot of time, maybe 3-4 days. Not only that, sometimes when we extract the analysis results, like the girder rotation, we have hundreds of girders, and extract the girder rotation result, sometimes we cannot extract to the text file. So in that case, we have to reduce the number of steps before we analyze the ground motions. But we have to write we have a program to reduce the number of steps, but not spoiling the ground motion pattern. And after we reduce the step, and then we construct the response spectrum curve and compare the response spectrum curves before and after after changing the time step. Then if they are okay, we analyze it. So normally we run the time step about 2,000 to 6,000 time steps. So nonlinear time history analysis, it is quite complicated process. So we have to learn the modeling and interpretation of the analysis results from our experience. That's all for today for the nonlinear analysis and modeling in Perform 3D. If you have any question about that, we are glad for the questions.
For the model that you have, how long does it take to run?
About 1 day. Yes, around 1 to 2 days. That one, the ground number of step is quite.
And for this loop, why is it depends on where am I on the time step it changes? It's not continuous. This loop, right? If you change the location of then you plot, it's different.
This one is the loop that you're seeing over here is basically the loop for the girder rotation, right?
Yeah.
So if I am right, okay, let's say if the red cursor is here, that means that the amount of force at this time step is this much. This much is the moment in the girder at this time step. If I continue to plotting it, you will see that the force is increasing. So with every time step, the force continues to change, and then there will be a time step where it has already yielded, and then there will be time steps where you will get some higher rotation demand. Right? So something like that. So because the force is not constant, the demand force is not constant, so we cannot have just one result, right? We have to have many results. So this is just a simple plot, just to demonstrate what happens to a girder in Shear.
How do you make the animation? How do you make the animation?
Press enter.
Press enter?
Yes, enter continuously.
Oh,
It's okay?
One more thing that we should be mentioning over here right now is that sometimes when you want to plot the residual drift, you have to increase the time of the analysis. So, say for example, let me just do like this. Okay. So if you have a ground motion, I'm selecting the central ground motion over here, you can see that the time step, the duration of the ground motion mentioned over here in this tab is 25 seconds. So the duration of the time is 25 seconds, right? So what you do is that you just increase the time of the analysis. So if this is 25, if you want to increase the time step of the analysis itself, what happens is that after the duration of the ground motion finishes, all of the data becomes 0. So then no more force is being applied, right? So you just simply increase the time of the analysis. There's no need to change the time of the ground motion itself, right? For you to have a residual drift that is after some free vibration cycles, right? Only that.
And after we apply the gravity loads in perform 3D model and mass, we have to check the total weight of the building along the height of the building, as well as the model analysis results. Because if we mistakenly assign the gravity loads in certain floors, we can detect from the comparison. So we have to run ETAPS model with the detailed gravity floor loads and our simplified load application with in the perform 3D model. So we have to check the gravity loads for each floor.
What's the reaction? Story shear?
Yes, story shear. Just plot the story shear of dead load plus 25% live load combination along the height from ETAPS and along the height from perform 3D. If two curves are not matching in some level, it suddenly increase. So we have to check that level loading application. If we have the secondary beams in the model, which are resting on the main girders, in perform 3D model, it is better not to model the secondary beams, because if we model the secondary beams resting on the girder, we have to divide the girder in the model, physically divide. So when we apply the hinges, we have to apply, if we divide that girder, we have to apply one side at the left end, one side at the right end only. So it will be complicated when you assign the, when you create the compound section and assign on those girders. So for the secondary beam, we just apply the point load on the girder to represent. For the slab modeling in Perform 3D, we just model that slab to consider the in-plane stiffness of the slab. We do not, in Perform 3D, we can transfer the weight of the slab to the vertical member, but only from that 4 nodes. So if we apply that, for example, the slab is supported by the 4 beams at the parameter. If we apply if we want to transfer the load self-weight of the slab to the beams, the program cannot transfer because of the 4 nodes, it will transfer directly to the column, not to the beam. So what we normally do is we model the slab but change the weight